Now let us start by considering an important test bed for reasonings, and it's known as the visual question answerings. Here's a simple example. So given the image of the object lying on the ground, the question is, what colors is the thing with the same size as the blue cylinder? So the question is not easy to answer, and the correct answer is actually green, not the blue, because it requires multiple step reasoning. First, we find the blue cylinders in the picture, and then we locate the object at the same size, which is the green object that's next to the yellow cylinder, and we determine that determine its color, which is green in this case. The straightforward applying neural network to this case may fail because it have no notion of the composabilities in the questions and have no notion of the multi-step reasonings. So topics of the visual questions ring is indeed very interesting. It's very fascinating to serve as test bed for the next phase of deep learnings, because it covers at least 4 important topics, 4 important AI areas. One is machine learning, another one is reasoning, and the third one comes to visions, and the fourth one is natural language processing. Right? In machine learning, we have to find a way to learn to extract information from the questions and extract pattern from the image, and then learn a way to change those patterns and matching and reasoning and relations in the correct answer, the correct manner, so that we can compute the right answer. For reasonings, we need to find a way to encode the concept of the program synthesis. It means that we call only the right kind of computational given the questions. And if we want to go further, we have to find a way to incorporate common sense reasonings and making use of the inference among the relation and among time. And come to vision, we need to solve the hard problems of object detections, discovery, computing the scene graphs, and action graphs through times. And in language processing, we need to find a way to process the symbols native in the language and try to find a way to bind the symbol to the actual objects in the image or videos. So we need to find a way to pass the question in the correct way so that we can build the computational graph accordingly. And we need to find a way to ensure that we can generalize to similar question, but using different symbols. And that is known as the systematic generalizations. So all the requirements are largely missing in our current deep learning literature. So an important approach to reasoning is known as the learning to reasons, and it draws the connection between machine learning and reasonings. So instead of dealing with reasoning as its own, we think of reasoning as a way, as a classification problems. And because of classification problems, we can use machine learning to learn that classifiers. So for the sake of comprehensiveness, let's recall that learning is the way to improve improve ourselves by experiencing more and more data and experience, so that we acquire the knowledge and skill to solve the problem, so that the performance of solving a particular problems is improving. Whereas reasoning is a process of deducing the knowledge, the new knowledge from the previous acquired knowledge in response to a query. Right? So it have to be produce something new in response to something, given the known things. Right? So it sound like different things. However, we can connect them up by using machine learning to improve the ability to decide if a inference is correct or not. So assume that the inference is done and we don't know whether it's correct or not. So we learn to determine if the inference is correct or not. Right? For example, given a video and the question is that what is a person doing before singing, right? And then the reasoning, learning to reason method is to determine if in the video the person turns before singing, right? So it become a binary classification problems. And combining these two things together, we may expect that reasoning, we can build a program just in time in response to query so that the reasoning may happen. And that's also a way to realize the concept of conditional computations, which means that we only call the right computation whenever we need to. So given the learning to reason is a feasible approach to reasonings, so why should we use deep learning for or neural network for the purpose? So that's good, interesting questions. And Leon Botu have very interesting answer. He argued that reasoning is not necessarily achieved by making logical inference. So he refutes the common belief of the old day that to be able to do reasoning, high-level reasoning, we have to come down to logics. Because logic is seem to be the most relevant structures that people think that humans may use to perform reasonings. But both tools argue that it's not actually the case, because whenever we see something, we think of something, we recognize some things, there's no evidence that we do the formal analysis because we just know the answer. And the formal analysis might be needed for something else, but most of the thing in the real world, we do not need the formal analysis. And there's no evidence that we actually perform logical reasoning within our head. So he has suggested that there may exist a middle layers already a kind of reasoning, but not yet formal or logical. From that argument, he proposed that there should be a continuities between the inference mechanisms and similarly connecting together trainable learning systems. And by trainable learning systems, we may refer to the neural networks that have the weights so we can tune through the backpropagations. And if that's the case, then we may be able to build the reasoning system out of neural networks by connecting different modules, each of which perform different things together in the correct way, and maybe train together to improve the performance of the system. And to both to the central reasoning is the compositional rules to guide the combination of the model to address a new task. So to him, reasoning is nothing but connecting the modules in the right way, and those modules are trainable, and it make neural network to be a good candidate for reasoning. So we review here two possible approaches to neural reasonings. One approach is called, I call the implicit reasoning. So it find a way to implicitly change the predicate to recurrence. So recall that recurrent neural networks can be as powerful as a Turing machine if we know a way to rearrange the data so that it look like a recurrent networks. So liberating from that concepts, we can have the implicit training to recurrent networks. It does by stepwise attentions to the relevant concept and relations, given the query. So it have to be linked between the queries and concept and relations. And then it run the recurrent operation so that the entire process of concept refinements and combinations are iteratively done by recurrent systems. And we may use a working memory to enable that refinements in a long period of multiple steps. And then finally, after enough refinements, we can compute the answer from the last state of the memories and maybe the embedding of the questions. On the other hand, another way to do so is by building the explicit computational program. So we assume that there is a set of modules, each of which perform a predefined operations or functions. So a question is first passed into a symbolic programs, and that program would guide the building and connecting of the module together to perform to arrive at a computational system. And then we run the program to compute an answer. Let us start with the first implicit approach by quickly reviewing a strong reasoning system called magnet. And MAG here stands for um, the memories, attention, and control. So the magnet is actually a recurrent system. Except steps, the recurrent system perform three operations. It read from the memories and write into the memories and updating the controlling process. Okay. So the controlling process would consult the queries and then match the queries into with one of the element in the memory, and then combining the new evidence into um, its own internal memory, and then repeating the entire process. So in effect, it tried to match the keywords in the questions with the element in the knowledge base that we want to consult. And in this case, in this particular visual questioning case, the knowledge base is nothing but an output of CNN. So recall that CNN is operating on the grid systems. And through poolings, we attracting the features in each of the cells in the grid systems. So for example, an image of size 100 by 100 can be um, processed to have something like 15 by 15 cells. So we consider each of the cells an element of the visual knowledge base. And the system, the MAC system, is try to find which cell corresponding to what word in the questions. So the entire process is repeated over time. And finally, we compute the answer using a classifier, using your knowledge from the memories and the question embedding. This is a very generic mechanism for finding interaction between the query, which is a set, and the knowledge base, which is also a set. And regardless of what the nature of the actual content of the set, we can still perform the max operations and produce the answer that corresponds to the queries in the knowledge base. So following Marx, there was a recent work by our colleagues and myself. It's called the LogNet. And LogNet tried to improve upon the Marx by realizing that we need a way to perform the explicit binding between the language and the objects. And second recognition is that we need a way to explicitly compute the relationship between objects if we want to answer the relational question and compositional questions. Okay. And we use recurrent networks with the relational interaction between objects and the queries in a recurrent way to refine the object representation and define the different relation between objects depending on the query, right? And at the end of the day, we build a single network that are differentiable end to end. So here is the architecture of the network on the top figures. So the building blocks of the networks. So it takes the input of the image. We had multiple objects in there, and the question which have could be long and complex. So it go through a object recognition system. In this case, faster RCNN to detect an objects, set of objects in the image, and it's used by LSTM, so bidirectional LSTM, to process the image to have the embeddings of the except the words and embedding of the questions. And the process is repeated with multiple units. Except the time we build one relational graphs between the objects in response to a particular input in the query. And each of the graph it tells a graph convolutional net which I reviews in the first part of the tutorial. And the another novelty here that the graph have the skip connection that allows us to refine the objects in many steps and still be able to train it. Then as a result, the network itself is very deep. It have more than 100 or up to 200 layer of the graph convolutional net. And in each of the steps, it do two things. It connects the object together, and it's try to bind the keywords in the query into the objects of the scene. And finally, it pulls information from the that's processed together with the information from the queries to compute the answer. And here are some example of how the attention to from word to the object works. So for example, if the word is colors, then of course, it need to attend to multiple objects because all objects have colors, right? But because it have other words like metals and cues and things, it try to attend to those the objects would have those characteristics. And then if the keyword is same, then it try to connect to the objects that may be of comparable size, right, or colors, depending on what the nature of question is. In this case, it's um, the same internal colors, right? So that was an example of how the iterative reasoning works in a deep neural networks. Another observation is that transformer, as as it reviews in the first part of the tutorial, it actually performing an implicit reasonings. Why? Because reasoning can be thought as a way to minimize certain energies or free energies. So for those who are familiar with the graphical models, the classic belief progression algorithm actually minimize the so-called Bithy free energies. And belief progression is a way to perform reasoning on the probabilistic graphical models to compute the marginal relationship between a couple of one or more variables. So transformer actually a relational iterative refinement techniques. And that itself gives us a way to perform the implicit relational reasonings. So recall that we have shown that the transformer itself is a way to minimize a certain energies, which Ramsauer and Collins have proved that actually is the case. So it suggests that transformer is a good candidate for relational reasonings, and the way it works actually performing certain kind of reasonings without declaring it. So that explains the success of transformer in the question answerings. So here's one examples. Right. So here example of using bird, but recall that bird is actually a transformer trained in a certain way by masking out certain part and reconstructing that part. So deep down, it's still a transformer. So the way it works in this particular task is that the task is we have a text and the questions. We have a question and we identify the answer within the text that's corresponding to questions. So the way it works is to arrange the question and the text in the same manner so that we can process a token from the text and question in the same way and build the relationships between the token using the cell attention mechanisms. And that process, if we compute multiple times, it turned out to be the optimized certain energy function as the reason we have shown before. And in the process, the token refines so that we can point out which tokens is the start or which token is the end of the answer of the questions. Another way to make BERT and transformer works for visual question answering is the current work that's submitted to the ICOR this year. So it arranges the objects in the videos and tokens in the questions in the same manner. So the video itself, it's attracted using the unsupervised learning techniques called MONET, so that we have the representation of objects. And the tokens arranged in the same way so that we have the embedding of the tokens. In the end, we have the each of token, all the objects in the video are represented as a embedding vector. And then transformers are applied in the same way across the modalities. And the novelty here that they add the BERT-like training so that we can have the self-supervised training, and at the same time we have the supervised trainings. So to recall that self-supervised training and supervised trainings are similar in the operations, only different is that in supervised training we have the external labels, and in self-supervised training we don't have external labels. We have the mask input as a label, but in terms of optimization, it performs a similarly. Another approach is explicit reasonings, so that we build the programs that generates the answer explicitly. So in this case, here's an example. So if the question is what's the colors of the 5 hydrants, then the question is passed to the question parser. So we have 2 sub-modules. One is the filter that's selecting the objects. Another one is the query that's selecting the color. Right? And then these 2 modules are chained together to predict the answer. So this system, NSCL system, have multiple interesting components. One is concept learners, and it attracts the object proposal from the image using so that we have the feature vectors. Then using that feature vector to run a subprogram set to match to find out the shape of the objects and find out the shape and then compute the embedding of the concepts. And then once we build the models and the concepts and the models, the program itself is built to by chaining the program in the correct way, and the order of chaining determined by the question parser. Right? And then having the programs, we execute the program to refine the representation of the input of each of the models, and finally compute the answer. So the main difference between the implicit and explicit approaches is that in the implicit, all the relation and the concepts match and change to attention mechanisms, and that can be soft because there's no clear boundary between those things. Whereas in the explicit one, the programs are discrete, and we need a way to pass the question into the discrete programs. And because of discrete, we might need to employ reinforcement learning techniques to handle the entire program rather than one step at a time. So far, the tools are working very well in the synthetics, both synthetics, but it looked like the implicit one is a little bit more robust because it doesn't doesn't require very strong explicit sentence parser. Right. So it's the end of the reasoning subtopics, and for the rest of the talks, I'm gonna quickly review what is there in building a socializable agents, because so far we have more focus on building the reasoning system or learning in reasoning system for single agents. And the question is that if we are to succeed in building AI, then AI have to be social, right? At least AI have to live with human, and AI have to live with each other, so that we can have the entire system, ecosystem of multiple agents and multiple humans. And to be able to do so, then AI have to be able to understand what are the AI thinking, also what human thinkings, right? So that is the topic of the core theory of mind. So far we have talked about question answerings, and in a sense, it's quite straightforward and objectives. Because the questioner says that I will ask about what I don't know, and the answer is very true to itself. I will answer what I know. I try to understand you, and I try to answer what I know. Right? There's no difficult in guessing what other people want and read behind the lies. Right? However, in the real life, the situation is not that simple, and it's not that objectives. It's more subjectives. Like for example, questioners they may think I will ask on a question that I think the answer may know, and the answer one is that, oh, this may be what I think they want me to answer. Right? The answer that person two may think I will answer only what I think they can think I can. Right? So I guess what you think I can. So the situation is far beyond what we have done, where I have shown in up to this point, and now it requires us to expand the concept of agent, single agent to multiple agent, and expand the concept of single mind to the theory of mind, is that we built a theory of what other people thinking. So before we go into the technical detail, let's start from the classics example known as Sally and Ann test. And the settings like this. Normally, this one is setting is a synthetic scenario that tests the theory of my capability of the young child. So the situation like this: we have Sally, and Sally has a basket, and we have Anne, and Anne has a box, right? First, the Sally put her cakes into her basket, and then Sally go out of the rooms, right? Um, and Anne, in absence of Sally, takes her cakes out of the basket and put into Anne's box, right? So then Sally come back to the room, right? So questions we ask the kid while observing this scenario is that where is the cakes? And probably the answer would be in the box, right? But the more difficult question is that where would you think Sally think the cake is? And if the child is very young, I think under 3 or 2, the child mostly say that Sally thinks in the box. Whereas the older child and the adults know that Sally must have think that the cake still in the basket because she didn't see what Anne did to her cake, right? So the thing here that the young child may have no theory of what Sally may think, but the adults have built that capabilities. The question is that can you build an AI system that have the same capabilities of an adult or larger kit, bigger kit, in inferring what other people might think, right? And more specifically, can you build a neural networks to do so? So in another situation, it's called social dilemmas, and one of classic is called stack hunt games, and it works like this. There are two teams going out for huntings, so they may choose to cooperate and or not. If they do cooperate, they have the chance to catch a bigger animals, the stacks, right? But if you don't want to cooperate, they can may choose to hunt the hare, right? But the problem is that if you hunt the hare, then it's there the stack away. Then we don't have the big rewards. But if we don't, if we cooperate, then we have to um, ignore the chance of catching the hare, right? But then if the team or person is selfish, they may catch the hare and pretend to cooperate to catch the stacks. And another team or person may not know that. Um, and we know that humans are social animals, and we know that humans learn to cooperate very well. Sometimes to the point that we sacrifice our own benefit to serve the greater good of the community. Um, so the idea to solve these problems that we may need to build a way to encourage people to cooperate, even if they lose um, their individual gains, right? And of course, it's to be able to do so. One of the way is to build the theory of mind into the agents, because they may think on the other's behalf what they may think. Right? So one of the early attempts to bring the neural machine learning neural networks into the theory of mind is the what's called machine theory of mind by DeMay. And the machinery have its recurrent networks, and it have two parts. One is the character networks, and another one is the mental net. And then the prediction net, right? The character net observe the past histories and estimate what the other person might may behave. And the mental net observes the current trajectories and estimate what the person thinking. And given the state, the predictions pull the information from the character net and the information from the mental net and the current state to predictions. It predicts the next action probably of the other person, and it might predict the goal that the person may achieve. Right? I'm not going to detail how it works and what the tests are, but bear in mind that this it's one of the successful attempt to model the theory of minds using neural networks. So the next one, I'm going to show an example of how theory of mind works in the situations of social dilemmas. So recall that we have the stack and gun games, and we need to build the agent to cooperate to for that the system to gain better than the system that doesn't cooperate, right? So that is new kind of agent called Tumaga, and it stands for theory of mind agent with guilt aversions. So guilt is a concept showing that we may experience certain loss in our feelings or utilities if we believe that we have hurt the other, you may have harmed the other in certain way. Right? So guilt don't need to be external. It's internal. So it serves that intrinsic reward, intrinsic motivation for us to stick with other and do good thing to other. So the Tomaga, what Tomaga did is that it observed the state and build a belief function of the other. And the belief function can be the first order and what the other may think and act. And it could be the second order that we believe the other may think about what we think, right? So combining these two elements together with the guilt functions, here we implement the guilt as the penalty to the rewards, and it's a kind of reshapings. So that if we believe that we have caused the harm by acting in certain way, then we penalize ourselves a bit. So the reward is now it's the total of the material rewards for an actions minus the guilt loss. If we believe that we have caused certain harm to the other. That systems have been shown to work very well in the social dilemma games. Whereas there's no way we can train the standard recurrent, deep recurrent neural networks to achieve the target of cooperative behavior. So that to give you an idea that we actually can build the theory of mind into the agents, and we can build the social functionalities like guilt aversions into the neural networks, and um, make the agent to perform socially. Right. So up to this point, I have briefly mentioned how neural network can implement the theory of mind and how it may works in the situation where we need the cooperating between agents. And it's time to wrap up what we have covered on this second part. So this tutorial have two parts. One is I call deep learning version 1, and the second one is what I call deep learning version 2. And roughly, deep learning version 1 is related to system 1 in the dual system theory, where we have strong pattern recognition mechanisms, and we can run fast and multiple processes at the same time. But we still do not have to make a way to represent and perform analytical reasonings, which is a core function of system 2. And the key of the system 2 is that it is hypothetical in the sense that it do not need to be directly linked to the patterns of the system one. System one is normally stick to the real world, and the concept it attracts is grounded to certain signals from the real world. Whereas in the system two, we do not need to ground it to the realities, and still be able to connect the abstract concept together in certain way. And to be able to handle system two and partly dealing with system one, we have shown that we need a mechanism um, to perform the memory operations so that we can store, retrieve, and manipulate fact semantics, event relations, and intermediate results in the long computational process. So that is a picture that I think that might be um, relevant for the discussion of the next steps of deep learning, which I call deep learning version 2. So to summarize, I have covered the following topics. The first part of the talks, I cover the classic models, starting from the perceptions to end up with recurrent networks. And then I cover the latest deployment in transformer. And one of the hottest topic of the day is graphical neural networks. And then cover the deep unsupervised learnings. And then I move on to the second part of the talks, which I call the deep learning version 2. I provide a systematic views of how deep this version 2 might happen, whereas we have the system for reasoning and system for the memories. And then I quickly give some glimpse into the current works called theory of minds, where we want to build an agent that live with other agents and try to think what other agent thinks. So we have reached the end of the talks. Thank you very much, and I hope that the tutorial give you the broad picture of what deep learning is about and what may happen in the next few years that may define the next phase of deep learning. Thank you very much for attending.